Good morning. Wake everybody up. So, how many of you were in Rohan Kumar's session yesterday? Okay. How many of you have heard the name hyperscale? Okay, good. How many of you have heard the name Socrates in relation to a feature of SQL? Okay. So, hyperscale is a new feature that I'll be talking about today. For the last 2.5 years, we used the project name Socrates to refer to this development. So you'll hear me slip back and forth because I haven't quite gotten used to calling it hyperscale all the time. So if you hear me say Socrates, mentally translate it into hyperscale and we'll be good. Okay? So just to set some context, this is an Azure SQL Database feature. So the Azure Relational Database services as a whole have this develop once, run on-premise or in the cloud using your favorite database engine. And there's a lot behind that. We have Azure SQL Database, SQL Server on Azure virtual machines. Then we have Azure Database for MySQL, Postgres, and now MariaDB. For the SQL part of that, it's a SQL Server and Azure SQL Database, it's important to understand that we have kind of a unique position in that we have only one code base. There's no separate Azure SQL Database code versus SQL Server. It's all one code base. Just like you load an Enterprise Edition license, you get one set of behaviors. You load standard, you get a different set. When we deploy into the cloud, it tweaks the behaviors a bit, but it's all based on the same code. We update the bits in Azure about once every month or so, and new features, as they're ready, will pop up in Azure throughout the months. And about every couple of years, we'll take the current state of that tree and ship it out on-premise as a version of SQL Server. So you'll see features pop up first in Azure and then move to SQL Server on-premise. But through it all, it's all the same code, so it's a very consistent experience across on-premise and the cloud. We've investing a lot in enabling a hybrid experience because in our experience talking to lots of customers, most customers have some of their data on-premise and some in the cloud, and for good reasons on both parts. So we want to make the experience of bridging that divide as smooth as we possibly can. So for all of these Azure offerings, they have some virtues. They have intelligent features, so we have intelligence built into the Azure platform in the form of protection, performance. So we're using AI within the Azure infrastructure to look for patterns that might indicate that someone's trying to attack your database, and also to look for performance issues where we can tweak things and tune your database and make it go better. When we make one of those adjustments, we continue to monitor the effect of that to make sure it was actually a win, and if it wasn't, we'll back it out. Flexibility. Hyperscale is a prime example of that, as you'll see over the next hour or so. Have elastic scaling, the ability to scale up and down as your performance needs dictate, resource governance to keep within pools, to keep from having one database overwhelm all the others. And trusted, of course. We have always encrypted with Secure Enclave as a new feature. If you're in the security area, you need to learn about that. Business continuity with HANDR, industry compliance certifications, and enterprise security isolation. So you can have complete isolation between your environments. So with the Azure SQL Database, we have multiple deployment options. You can have a single database, which is what we first came out with, which is you get a connection to a database. And the performance of queries should be completely compatible with SQL Server, but you don't get to access any of the other features within a typical SQL instance. So as long as you have a workload that can be confined within a single database, that's a great option. It's really flexible, it's cost effective, you can scale it through a wide range of capacities. Elastic Pool is, you also have a connection to a single database, but that database lives within a pool of resources. So if you have a situation where you have, say, multi-tenant, where each tenant gets its own databases, you can put all those databases in a pool, and generally they're not all going to spike at the same time. So you don't have to size the pool for the aggregate of all the databases spiking. You can size it to handle the common workload plus one or two databases spiking and save a significant amount of money that way. Managed Instance is a feature that we just announced GA yesterday. It's been in public preview for some time. Managed Instance gets you a connection into a SQL instance that is fully managed. So you get the full richness of surface area of a SQL instance. You have multiple databases, cross-database transactions, you have agent jobs, you have all the richness of a SQL instance without the headaches of managing it, because it's still on our platform, we manage it, we do backups for you, all of that is taken care of. So it's a very low friction way to get into the PaaS services, because there's virtually no friction there. Question?
How about with the managed intelligence? There's been an issue earlier with the intelligence options in the management studio.
So the question is, what about managed instance with IntelliSense? I'm not an managed instance expert. They are here. There's a talk specific to that, and we'll be down at the booth as well. So find Drazen. So we have a lot of announcements going on this week. Managed Instance, GA, Hyperscale going public preview as of October 1st. Reserve capacity, advanced threat detection, we have vulnerability assessment, GA. Data classification, always encrypted with secure enclaves. Intelligent databases, we have intelligent QP and approximate QP enhancements. I spoke to that yesterday. And on Friday, we'll be talking about SQL Graph enhancements. Enterprise reliability, have accelerated database recovery, parallel PFS updates, and resumable online index create and rebuild, which is a pretty cool feature. In the migration services, we have online migration to managed instance in preview, online migration to Azure Database for Postgres and MySQL, and offline migration to managed instance, which is GA. So a lot of stuff. We've been busy. The SQL database team has been putting in a lot of hours getting all this stuff ready, and we're really excited to get to tell you guys all about it. So Hyperscale is Azure SQL Database, but on a different storage layer. And I'll get into lots of details about how that works and what it's about. But one of the virtues that it has is it can handle very, very large sets of data. So how many people have dealt with very large databases, VLDBs? Okay. What are some of the headaches you see? Backup operations. What was it? Indexing. What else? What other headaches do you have relative to it being that big? Performance, not performing well. Anything else? Transaction log being full, yep. So Hyperscale is designed to provide a very smooth VLDB performance in a fully managed environment. So anything that's size of data operations can be a big problem, right? So operations that take a long time, days in some cases, when you have one of those operations ongoing, even if it's an online operation, it's going to degrade performance because you're moving a lot of bytes. Can cause outages and downtime. What does it take to provision more storage if you run out of space on one of those databases? You're going to be rolling in another SAN if you're on-premise, or adding to it, reconfiguring all your storage, that's not, and you better get it right. Scaling compute can also be challenging. If you run out of horsepower on the box on premise, you're talking about either doing a major modification to the system as it sits, which is a downtime, obviously, or rolling in a whole new system, which is even more churn. And then you have the economics of sizing for peak. If you're dealing with a really huge data set, when that spikes, that can be a lot of horsepower it needs. If you have to size for the biggest peak you might expect, plus some margin, you're paying for that all the time. It'd be nice to be able to just pay for it when you need it, right? So that's kind of what we're giving as well. Imagine a world where a cloud database supports 100 terabytes and more. You'll hear 100 terabytes a bunch of times in this talk and in others if you listen to talks about hyperscale. The significance of 100 terabytes is it's a nice round number. And that's about as far as we've tested so far. There's nothing architecturally that limits it, basically at all. We can scale as far as you want to scale. There's few to no size of data operations. I'll get into how we pull that off in a bit, and I'll show you what it looks like. Backups have zero performance impact of a 50 terabyte database without noticing it. In fact, we do it for you, so you don't even notice when it happens. Restores are extremely fast and, more to the point, constant time. So what do I mean by constant time? Constant time means that it will take you the same time to do a restore whether you're dealing with 5 terabytes, 10 terabytes, 50 terabytes, 100 terabytes. That's a bold claim. How many think I can back that up? So we'll see later on. Scale up and down happens in minutes, not hours, for both storage and compute. One of the interesting facets, I said that you can scale up to 100 terabytes and more. When you provision a hyperscale database, there is no max database size setting. It's not there. Just as you add more data, we'll grow what we have to grow on the back end to accommodate it. You pay for the storage that you're using. So even if we have to add another piece of hardware that gives us another terabyte on the back end, you'll pay for the portion of that you're using. So you don't have to pay for another terabyte just because we add another terabyte on the back end. So what's hyperscale? It's a new storage layer under the database. So we have preserved the query engine. There's no change to the portions of SQL that deal with executing your queries. The behavior is going to be exactly the same as Azure SQL Database. It just will deal with more data. All the secret sauce, all the magic happens in the storage layer. It's architected from the cloud, for the cloud from the ground up. So that means that when we looked at re-implementing the storage layer underneath SQL, we took into account cloud architectures and capabilities. So there's a lot of things that clouds bring to the table in terms of flexibility, the ability to move things around. We're taking advantage of that, and we designed for that through all that. So when I said that features start in Azure and make their way to the on-premise world, this is probably an exception because it really relies on the cloud architecture. It would be possible to do on-premise, but a lot of it has to do with the orchestration layers and the control plane within Azure to spin up new VMs for different purposes. And we don't have that. We can't count on exactly how that's going to behave in your environment. It's fully compatible with Azure SQL Database. As I said, we haven't changed the query engine at all. So you shouldn't notice any change outside of maybe a performance boost in some cases. Hyperscale's no limits. The marketing guys and actually LCA, the legal department, get twitchy when I say no limits because that's a bold claim. So I'll say that theoretically, there are no limits. Practically, there's a limited number of bytes in the world, so there's a limit somewhere. But for practical purposes, there's no limits in how far you can scale this thing. It's VLDB size without the VLDB headaches. So we're trying to take away all the things that you mentioned earlier as pain points of dealing with and managing a very large database, and support for 100 terabytes plus. Hyperscale's Azure SQL Database. So I'm going to be driving this point home. It is Azure SQL Database for all purposes of compatibility, behavior. It's just the same as Premium or even Standard Edition. It's going to behave the same. No new syntax, no new restrictions. In fact, much fewer restrictions. No changes to your queries in either required syntax or behavior. It's virtually without limits, freely scalable, so you can scale up and down. How many people are aware of the new vCore model for provisioning Azure SQL Database? Okay, Hyperscale is only available in that model. It didn't make sense to backfit it to the old DTU model. DTUs were a really handy construct for abstracting the hardware behind the capabilities we're selling you. So the idea was to give you a unit of computing power that would be constant regardless of what generation hardware we put into the back end. So if we replaced it with a newer generation, the DTU levels would be roughly constant. Turns out it added more confusion than it helped. So we're going to a model where we separately provision storage, memory, and cores. So you're paying, we call it the vCore model because you can scale by the number of vCores. So Hyperscale is sold in that model. You scale the vCores to whatever you need for your processing. Scale them back down. It's designed from the bottom up for the cloud. Operation time, backup, scale up and down are not proportional to the size. I want to get that through. Take full advantage of cloud architectures without compromising compatibility or performance. A lot of times when we talk about moving to a new architecture, there's a lot of adjustments you have to make. There's a lot of pain to get there. We're trying to take all that away from this. So what is Hyperscale? It's a cost-effective VLDB SQL PaaS offering from Microsoft. High performance, scalable, designed from the ground up for demanding needs of mission-critical VLDB apps. So this is what we're talking about. So how do we do it? What's the approach we took in Hyperscale? We started by splitting the SQL engine. So SQL engine has historically had a lot of different components to it, but in big chunks, we had the query engine and the storage engine. The query engine dealt with all the behaviors of executing queries, and all that had to do with the behavior of the query against the data. Storage engine had to do with managing the data on storage, shuffling pages between disk and buffer pool, managing all that stuff. So we kept the query engine intact. We didn't really change the query engine. We replaced the storage engine layer of SQL with a new architecture, and that's where Hyperscale comes in. So we now have the query engine in a compute server or a series of compute servers, and we have a set of separate servers that serve up the pages, actually, and they can scale independently. We physically separate compute and storage. So again, we have compute servers for the query engine, and then page servers for serving out the data pages, and then a separate log service for dealing with the log traffic to make sure that's optimal as well. And by doing it that way, we can just, as the database gets bigger, we can just add on another page server to get more capacity. So no one page server gets overrun by this huge bloated amount of storage. The compute servers aren't burdened with all that storage. They only deal with what the queries need. So no one piece gets bogged down with the huge volume of data, and that's how we can really scale as efficiently as we do. So I'll go through this diagram in more detail in a bit, but I just wanted to give you some context for the things that we'll be talking about between now and then. So you see the read and write and read only. So you have one of those servers that's the primary, just like in an availability group. So one of those compute nodes can handle write access, read and write access, and you have at least one and up to 15 readable secondaries scaled out. And remember, that's just compute. We're not duplicating storage there. Page servers is in that middle box on the left-hand side. So you have each page server manages the pages that make up about a terabyte's worth of data. It's just a nice round number. So the interface between the compute engine, the query engine, and the page servers is in the get me this page access. It's very easy to know which page server has which page because internally page IDs have always been the file number, a composite of file number and page within the file. We model each page server as a file, data file in SQL Server, so from the page ID we know exactly which page server has that page. We can go directly to it. The ultimate back-end storage is in Azure Blob Storage because that gives us triply redundant storage that's independent of any one of these servers. It's a very stable platform. It also gives us the facility of having snapshots. So that's how we can do backups without impacting your workload at all. The backups happen in Azure Blob, and they're virtually no impact to Azure Blob. And the page servers also buffer that entirely because each page server has a local cache. Resilient Buffer Pool Extensions is the name we call it internally. But we have each terabyte page server has a terabyte of SSD that's local to it that caches all the data that it's going to manage. So you're never going all the way down to Azure Blob when you go to retrieve data. On the log side, log records go directly into a landing zone in Azure Premium Storage, which is very fast. The log service then forwards it to anyone that needs to update the pages involved in that log record. So the compute storage for any pages they have cached, the page server that owns that page will get updated that way. So this is kind of the high level of the architecture. As I said, we'll go deeper in a bit. If there are any questions, please feel free to ask questions as we go. Nope. Y'all understand it. Cool. I'm done. So we're going to go through some of the virtues we're bringing to the table here. Scalable. So scale quickly without concern for data size. That's an interesting capability. Data size and compute cores scale independently. You can scale a 50 terabyte database in minutes, and there's no size of data operations when you're scaling. So if you've dealt with premium databases, you know that when you're scaling that, we're copying the entire contents of your data to a new VM. So that's going to take some time. We don't do that here. And I'm going to show you. So this is the portal. I've got a database that is 50 terabytes. There's 50 terabytes of actual data in there. What's allocated storage is 54 terabytes. That's just the way it rounded out. So I've allocated 54 terabytes for this database. We pumped 50 terabytes of data into the database, and that took some time, let me tell you. I'm going to go into the configure. So you'll notice here that this is in the new vCores. When you're in hyperscale, you can't scale to the single databases. And that's something to consider is once you moved in your data into hyperscale, you can't just scale to move it back. It would be an export-import to get it out of the hyperscale environment. Of course, if you go over the max size of a singleton database, you can't get there anyway. So the operations that we first optimized for were getting into hyperscale. And I'll get into that, actually show you how that works in a bit. But for scaling, This is a 50 terabyte database that's currently running on 2 cores. If you're on Gen 4 hardware, you can get down to 1 core to manage 50 terabytes. So think about the economics of that. If you've got a very large data set that is only used periodically, you can park it for very little money. This is preview pricing with AHub benefits, but $300 a month for parking 50 terabytes in an accessible SQL database is pretty impressive. But there may come times when you actually have to use all that data and use it quickly. So for that, we just scale, just like you're used to. So set the scale up and apply. And now we have the scale operation that's going. So what's happening behind the covers, if you remember that architecture diagram where we had the compute servers, the original compute servers each were 2 core VMs, right? So what we're doing behind the scenes, you can think of that sort of like an availability group. It's not actually that, but it functions that way. We're adding another full set of replicas into that set, so it'll grow to double size with the higher capacity. So we're adding a bunch of 20 core VMs into that availability set. Once they're all up, caught up, and stable, we'll fail over to one of the larger VMs. So now your database is running on 20 cores instead of 2 cores, and then we'll just decommission the old VMs that were running on 1 or 2 cores. Make sense? Any questions on that? So that's how we accomplish scaling very quickly without moving any data. So scale operations typically take a couple minutes. I've got time to take a couple questions. Yeah. So the previous model was the query engine was not decoupled from storage and logs. That's true for premium databases. For standard edition databases, the storage is in Azure Storage, so it was separated. See if I can understand that. So right now you run into the situation where you over-provision to handle any possible spikes, so you don't get surprised by the spikes, and you end up paying a whole lot of money for a database that the majority of the time is running at 10, 20% capacity, and the other 80 or 90% of the capacity is wasted, and you end up paying way more than you should. Hyperscale helps that. We're already done. We've been done for a while. So that was scaling 50 terabytes. As that shows, we can scale fairly quickly and painlessly. And so during the failover, an active connection will drop and then come back up. And that's all that you're going to feel. So it does allow you to be fairly free in scaling up and down as long as your peaks are somewhat predictable. If you're already in the middle of the peak, obviously you're not going to want to take that hit. But a lot of times the business has cycles. So month end, year end, whatever, you scale up to handle all that processing. In the slow times, you scale down and save money. Managing VLDBs, backup and restore. So with the technology you've got today, how long do you think it would take you to restore a 50 terabyte database? Anybody have any guesses? 7 days? 7 days? with the technology you have. Technology you have. 2 weeks, maybe. It's going to take a long time. I'll show you what we can do. In the interest of time, I have recorded the restoring of that same 50 terabyte database, so I restored a copy of it. I've got a timer running, so we're just setting up, giving it a unique name, hit go, start the timer. So the timer is there so you can, so you're not, I'm not cheating, you know exactly how long it really took. I'm going to cut out some of the wait time because it's not really exciting in the middle of a presentation. I could have set it up and gone back to a previous restore and showed you how that looked. That would be another option, but this is interesting as well. So what's going on in the background is that we're taking one of those snapshots from the Azure storage, instantiating the snapshot on each of those blobs to be a new writable volume from the contents of snapshots. That's virtually instantaneous. And now we're provisioning another full set of page servers, so there's duplicates of each page server. So for a 50 terabyte database, that's 100 page servers, probably plus one or two. A new log server and a new set of compute, and then running recovery on the database when all that's up. So we just cut out some time. Not trying to be sneaky here, so I made it obvious where the cut was. You see the new copy of the database pop up in the list below for the server. And it's just, so the new database is instantiated. It's just coming online, finishing up cleanup. It'll take another few seconds here, but that's how quickly we can restore 50 terabytes. Waiting for that to pop up. So again, this is all within one virtual server. So just popping up, restoring another copy of that database, and it's done. 7 minutes, 51 seconds to restore 50 terabytes of data. That's an impressive feat. So the backup file was actually just snapshots of the Azure blob. So when you have blob storage, you can take snapshots of it, and then you can take one of the snapshots, which is a virtual snapshot of the data, and just instantiate it as a new writable disk. So is that the Azure Site Recovery? No, it's a different technology. It's a capability of Azure Blob Storage. Yeah, questions, good.
So you said that it's time constant restoration. So do all backup or restoration take 7 minutes?
So you said it was time constant. So do all backups or restores take 7 minutes? No, it's the point I was trying to get across is the time to do a restore isn't dependent on the volume of data. Actually, the time you request is probably not going to land exactly on one of those snapshots. So we're going to end up rolling forward to the time you request. So it's more proportional to that delta between the time we happen to take a snapshot and the time you requested to restore to, because that's the restore time. And in the back end, there's some variability in how long it takes to provision a set of servers for the different pieces of this, page servers and compute servers. Depends on how much we have to shuffle around. But again, that's just the internals of Azure. It's not dependent on the size of your data. That's another question. Am I able to do snapshots in a different region and do a restore in a different region. If you do geo secondaries, you do it there. But the snapshot exists where the storage is, and the storage exists by default in the region the database is. So you're not going to be able to do that. Just do a restore on a different region. Eventually. I don't think it's there yet. So it's just going into preview, public preview. So there's some pieces that aren't quite finished yet. Question? What if you only wanted to restore a few tables of the database? We'll give you the whole database, and you can take out of it what you need. It's quicker. It's actually quicker to do that than it would be to physically restore and stream. So if you only want a couple tables back in time, because of the mechanics of how we do it that fast, we have no idea what tables live within that Azure blob. So as you add data to tables, as we put in more pages, it just gets added to the next page server in line. So there's no way to physically differentiate what storage is associated with which tables. So the most efficient way to do that would be to do a restore, full restore of the database to another point in time, which is fairly quick and inexpensive, and then just copy across from one database to the other, select into. That will depend on managed instance integration, which is coming before we GA, so probably end of the year-ish, maybe. So the question is, do I have to have a separate backup schedule for Azure SQL DB versus Hyperscale? You don't schedule any of them. We do them for you. So for any Azure SQL database, the contract is, we'll take care of backing it up. You just tell us what point in time you want it restored to, and we'll take care of it. That's part of the SLA we guarantee. You don't set the frequency of the backup. We set whatever it takes to make it most efficient. Hyperscale, the snapshots are fairly frequent so that we never have to roll forward that much data. And it's very low cost to us to keep an extra snapshot around. There's another question. How far back do the snapshots go? I am not certain of this answer, so take the caveat here. I think it's 6 months. Any other questions? Yes?
How does this relate sort of longer term to the existing Azure SQL Premium and standard sort of architecture? I mean, it almost seems like this has a lot of benefits and can be beneficial downstream to tiers. Going forward with this architecture, viewed as sort of the future of those services as well. So are we going to get things like fast restores and fast scaling down on those service tiers as well, or will there even be those separate services?
So the question was, how does this relate to the existing service tiers, the standard and premium tiers? Is this going to filter down into those tiers? Right now, we view this as a third tier. So you have, what is the standard equivalent in vCore? General purpose. So in the vCore model, we have general purpose, standard equivalent, business critical, which is premium equivalent, and then hyperscale. So it's a third choice there. If it makes sense, we may filter it into some of the other offerings. Obviously, there's a lot more moving pieces for us to maintain in hyperscale. So it's really targeted at VLDB offerings, so very large databases. So that's where it's going to shine. If you've got a modest-sized database under a terabyte, it's probably going to be simpler to run it in the existing offerings. Question?
With the page servers, how much offloading does that do against your, like you get
So with the page servers, how much load does that take off of the CPU in your compute? So compared to a standard Azure SQL database where that one compute does everything. It's not terribly large. Most of the compute is taken up in query processing. So yeah, it does take away some of it. In the future, there's a lot of ideas floating around. We may try and push some of the filtering down into the page servers so that they don't have to return as much data, but that's a ways out there. Right now we're working on getting all of this buttoned up and solid. Yes? So how do you do point-in-time restores without doing log backups, or how do you manage the log backups? Is that the question? So I will get into that. The short answer is we don't do log backups. We just don't get rid of the log. One more. So what's the HA story if you're not doing availability groups? For compute, you have at least 2 servers up at all times. So if one dies, the other one is hot and ready to go. If you have more than that, obviously you have more resiliency. Each page server has a duplicate running as well. So if a page server dies, it's got a partner to just take over immediately with no interruption. Log server. So all the pieces have redundancy built in. Ultimately, the storage doesn't reside in any of those. It resides in Azure Blob. So if we have to rebuild everything, we can do it from scratch with no data loss. Okay. So high performance, low latency, high throughput for large databases. Backups are snapshot-based, rapid restore. So I'm going to do a performance comparison. So we've got general purpose, business critical, and hyperscale. With all this extra infrastructure, you might think that hyperscale is going to be significantly slower, but that turns out not to be the case. Okay, so this demo is not going to work, but I can show you what happened last time. So what this demo is it's a Spark cluster loading data into a P15, 4 gigabytes of data into hyperscale, and then into a P15. I went to start the Spark cluster this morning, and it's still pending, so I'm not going to be able to show you live, but we do have the results of the last run. So loading 4 terabytes into the hyperscale database took 40.2 seconds. That was last night when I was rehearsing. Loading that same data set, same mechanisms, into a P15 took 1.6 minutes. So in this instance, hyperscale was faster than a P15. So even with all that extra architecture, extra moving pieces, you're not taking any hit in speed. Reliability and availability, we've got multiple levels of redundancy like we just discussed when I was answering questions. So every component has redundancy built in, and ultimately we have the storage based on Azure Blob Storage, which is multiply redundant internal to itself in that service. So absolute worst case, we can rebuild everything based on the storage. No single points of failure. We have 4 nines availability. Ease of adoption. So we've got a whole different storage architecture here. So what would you expect it to take to get a database from, say, a P15 into hyperscale? What would you expect the operation to look like? Anybody? Export, import? When you're dealing with this many terabytes, that's pretty painful. What? Holidays? Polybase? So we've actually done some work to make sure that that's a painless operation for you. And I'll show you that. So I figure a P6 database, so 1,000 DTU database. And I've decided that this thing is going to grow farther, and I want it to be hyperscale. So go into the configure where we change the DTU settings. And you see your basic standard. Let me go back. Apparently I had used that database once before, so I'm going to make a new one. P9. No, premium. That's a P11. Once this database lands, I'll be moving it into Socrates. It'll take a little bit of time. Are there any questions? Yes? So will we see this technology trickle down to on-premise services like SQL Server 2019 or 2020 or whatever the next is? It's unlikely because a lot of what we do has to do with the control plane and the orchestration capabilities within Azure. So we're spinning up new VMs, new services, connecting them in, setting up the routing. So all of that is orchestration that's outside of the SQL engine that makes this stuff work. And we don't have control over your environment. So I don't know what it would take to create a new VM on a new piece of hardware in your infrastructure. So I can't automate that. Someday, maybe it'll be part of a larger package, but it's not going to happen soon. Yes? So can you expand on, you keep the log? I'll defer that. I've got some architecture slides I'm going to go through. I'm going to shortcut this. It's kind of just waiting, but just completed. Okay. Why am I not seeing? Of course. So move this database to Socrates, to hyperscale. Told you I'd slip. We go and shift into the new vCore models, choose hyperscale, choose whether I'm using Gen 4 or Gen 5 hardware. There's some differences between the generations of hardware, but that's a different talk. Gen 5 scales farther. You can go up to 80 vCores. Gen 4 ranges from 1 to 24 cores. You can scale from gen to gen. And I apply. And that's all it takes to move from premium to hyperscale. It's just another scale operation. So at this point, there is no going back. So we can't just scale back. It wasn't the highest priority in developing the feature. I don't know how much demand there will be for moving out of this environment. Certainly if you scale up to where we're designing this for very large databases, you can't scale back to Azure SQL Database because it won't go that big. If there's a lot of demand, we'll consider facilitating that. At this point, we probably won't. You can scale back from Gen 5 to Gen 4. You can scale from 80 cores down to 2 cores. All that flexibility you have. So you can scale freely between the generations and between the number of cores. So however makes sense to you. In any event, what we're doing is we're swapping a new set of compute nodes in. And it doesn't really matter to us whether we swap in a Gen 4 or Gen 5 compute node. Okay, so I had an error in scaling, which is actually a really good opportunity here. So with this database, if I go back into the configure blade, from premium, go up to, say, Gen 4 with 4 cores. Right here, save up to 55% with a license you already own. So this is how you apply the Azure hybrid use benefits. So you just click yes there. I confirm that I have a SQL license that allows me to do this, and your prices go down. And that's immediately reflected here. Okay? So this UI, this infrastructure doesn't know how many licenses you own. So in this, you're attesting that you have enough licenses to cover how far you're scaling. And we don't have the ability to bill some of the cores at one price and other cores at a different price. Maybe at some point. So that's how easy it is to migrate into hyperscale. It's not a big effort. So now we get into the architecture. So we have the components. We've got the query engine in the compute nodes. We have page servers with local SSD cache. Each page server manages about 1 terabyte's worth of pages. We have a log service that has its own local cache, and remote data storage in Azure Blob for ultimate reliability. So there are questions about how the log works. So I'll get into more detail with that now. So when the compute server, the primary compute server, takes an update, it's going to send the log records out just like it would in an always-on environment, but it goes to the log service, and specifically it lands in Azure Premium Storage immediately. So it writes immediately to an area in Azure Premium Storage. And latency for those writes is currently a couple milliseconds. So that's not bad for a remote write. Azure Premium Storage is fast. There's a new development within Azure Storage that we are kind of working hand in hand with Azure Storage Group. When that lands, that'll go down to sub-millisecond. So you have sub-millisecond log writes, even having it persisted remotely, which is pretty cool technology. The log service then destages the log in the background as a background operation into long-term storage using Azure Standard Storage. So you have the landing zone Azure Premium Storage is a limited amount of storage, and that gets constantly recycled. But the log is transferred from there into Azure Standard Storage, and it just keeps appending. And we'll eventually trim it out after about 6 months or so. But we keep a long range of log records in Azure Standard Storage. So if you're doing restore, we can go back to as far back as you want. And we have snapshots of that storage, so if you really need to go back farther, we can retrieve those records. But that gives you a lot of flexibility in your restore points. And again, we're going to take the snapshot in the page server blobs that's closest before your desired time, and then use the log in that long-term log storage to roll it forward to right now, or the point that you request. So does that answer the log questions, log management? Okay. And then for the page server, each page server, as I've said multiple times, manages a terabyte's worth of pages, and the interface is at the page level. So get me this page, it returns it. There's, right now in an Azure Hyperscale database, there's only one file group, so you don't get to divide things up into multiple file groups. What that gets us is the ability to just, as the files fill up, as the logical files fill up, which is the data under the page server, we can just add another set of page servers. So each page server is paired. You can see that here. So we'll just add another set of page servers, provision it seamlessly in the background. You never see any of that event happenings. That's how we grow it. There's no max size for the database. Just as you need more storage, we'll provision more page servers. And it's a pay as you go. So it's you pay for the storage that you're using. I think it's running 10 or 12 cents a gigabyte in preview. So that's the kind of range. The target for this is for it to land in between general purpose and business critical, or standard and premium. So it'll, price-wise, it'll land in between that. Capability-wise, it's significantly past premium. Any questions on how all that fits together? Okay. So hyperscale, very large database designed to support VLDBs, initially provisioned with a terabyte of storage to start, and auto increments in chunks of a terabyte up to 100 terabytes. But again, you're paying for the portion of that terabyte that you're using. You're not paying for another terabyte just because we allocated another terabyte. Pay-as-you-go storage costing model. You can monitor the usage through the portal. You can see how much of that storage you're actually using, just like you saw that database that I restored and scaled had 54 terabytes allocated, but it was using 50 and change. Long-term retention of backup restores for point-in-time restore scenarios. You can migrate to hyperscales fast and efficient. Into hyperscale will be fast and efficient using backup and restore once we land the integration with managed instance. Till that point, it's just like any other Azure SQL database. And again, we will be landing integration with managed instance before we go GA, likely within the calendar year, but I can't promise. Benefits: decoupling of storage, log, and compute. Scaling compute is a constant time operation because, again, it's just swapping in another set of servers with more capabilities or less capabilities, depending on which way you're going. Backup restore operations are no longer impact the perf because you're not doing significant I/O when you're doing it. Instantaneous file snapshot backups that are actually in the background, so you never even know that they're happening. They're happening every few minutes. Restores are not a size of data operation. We saw how that worked. We saw how that looks. Most of the time is spent provisioning another set of servers, and that's the part that would make it really difficult to land this in SQL Server, because that's a lot of what we do in hyperscale is all that provisioning work and orchestration in the control plane. Flexible topology. You can provision geo-replicas with no compute nodes. 1 core is the minimum. Perf and scale at its heart. Scale up and down. Adding compute is a constant time operation. Doesn't impact primary compute performance. So in other words, we're just bringing up another set of compute nodes, and you'll see a minor glitch when we do the failover, disconnect, reconnect. Compute nodes have local persistent cache, so not only do the page servers have a terabyte in SSD, the local servers have their own local cache. So the chances of you going over the network to a page are relatively low. The chances of you going to Azure Storage to get a page are virtually zero, because it should always come from the page server's SSD at worst case. Transaction commit latency is a few milliseconds, initial preview, eventually sub-millisecond. And supported log generation rate is around 100 megabytes per second. That's substantial throughput, right? And we've seen it above that. So we're talking being able to sustain a very heavy workload and just keep going. High availability, 4 nines availability as an SLA. Zone redundant storage will be available in initial preview. Data log reside in zone redundant storage, so the Azure storage we're using for this is zone redundant. Primary compute will have zone redundant storage as soon as customer configures a new secondary. Fault-tolerant architectures enable seamlessly recovering during failures across availability zones. So what does hyperscale bring to you? Mission-critical, high-performance scalability and reliability, seamlessly tune perf and scale, migrate on-premise databases to large databases to the cloud. So databases you couldn't move now, you can get into hyperscale. Apps in the cloud that are growing. So a lot of customers I've talked to have been reluctant to look at Azure SQL Database because they know that there's a 4 terabyte cap. And they're afraid that if my business grows too much, I'm boxed into a corner here. Now you aren't. Even if you go to premium database now, knowing that there's a 4 terabyte cap, you can just scale into hyperscale. So you know that there's a route out of that, and you don't have to worry about being boxed in. So it's, in that way, we call it future-proofing. You don't have to worry about that future state. You know you've got all the headroom you want. High transactional throughput and read scalability. You can scale reads with multiple readable secondaries. The primary will sustain very large update rates. Experience hyperscale yourself. Public preview starts October 1st. So as of October 1st, you can go to the portal and make your own hyperscale database. Preview pricing is about 50% of the expected GA pricing. That's what we typically do with public previews. Pricing will be somewhere between general purpose and business critical. Create a new hyperscale database. Scale an Azure SQL database into hyperscale. All of that stuff will be available to you starting in about a week. And this is a list of all the SQL database related breakout sessions. And that's what I have. I'm open to questions. Yes?
You're scaling with compute nodes or free compute nodes. Are you using containers to do that? And what is the impact on like the memory space of the queries as they occur? Are they shared? Are they specific to my database? So from a security perspective, like a financial department asked me, or a financial customer asked me, well, where is our database process? Is it on a shared floor?
So the question is, what's the isolation between replicas if I'm in a financial environment? It's as much isolation as you get with Azure SQL Database. They're completely separate VMs. There's no shared memory space. It may happen to live on the same physical hardware as someone else, but it's isolated. I'm not positive. I don't think we're using containers, but I'm not positive. Okay? One more question. So I didn't get all the what?
Do you recommend this model for database size or based off the application that's using the database?
So do I recommend this based on database size or application profile? Database size is a big criteria for it. It's actually more efficient doing OLTP operations than it is doing analytics at this point. We'll be working on that. But if you've got it, the ideal workload, I would think, would be HTAP, hybrid transactional analytical processing, where you're doing analytical querying across a live OLTP data set. And this way, your data set can be very, very large, and you can still keep up with the OLTP traffic. Is there a minimum size? You're probably not going to gain a lot if you've got a 50 gigabyte database. We're still learning what the performance profiles are at various scales. So mostly it's, if you're heading towards the VLDB range, it's definitely this. Okay, one more. Is there any change in the column store implementation? The query engine is completely unchanged. So it uses the same code for doing column stores as SQL Server. Okay, thanks. I'll be available for questions.